Hi everyone, I'm Higgins, a postdoc from the Armagh Observatory working with York Vink, and I would like to thank the organisers for the opportunity to talk about my work at this meeting. Today I'm going to discuss the importance of internal mixing on evolutionary channels of massive stars in terms of the upper red supergiant luminosity across multiple metallicities, and particularly how the indirect effects of stellar winds can interact with mixing processes and dominate the fates of massive stars. So to start with a general picture of massive star evolution, we know that in the mass range of say 10 to 30 solar masses, that massive stars evolve from the main sequence towards cool red supergiants during core helium burning, exploding as type 2p supernovae and collapsing to form either a neutron star or black hole. But on the left hand side here we can see a HR diagram with evolutionary tracks of 20 to 60 solar mass stars with a theoretical Humphreys-Davidson limit shown in green, where stars stop evolving redwards and instead evolve bluewards as a Wolf-Rayet star. And the relative positions of these different evolutionary stages are sensitive to the metallicity, internal mixing and mass loss prescriptions. Now, the upper luminosity of red supergiants is considered to be a long-standing problem in connecting the theory to observations, since theory would predict that metallicity-dependent winds would dominate the evolution of massive stars, causing a higher red supergiant luminosity limit at lower metallicities. But recent observations by Davies et al. 2018 suggested that the LMC and SMC had a similar luminosity cutoff of around 5.5, with separate estimates of about 5.8 for the galaxy at the time. This change in evolutionary channels is important for comparing populations of blue and red supergiants or supernovae progenitors with population synthesis models, but this turning point is also considered to be highly sensitive to mass loss. We find that the combined analysis of the effects of stellar winds and internal mixing can determine which process dominates the bluewards evolution above a certain luminosity at each metallicity. This is a structure diagram of a 60 solar mass star evolving with time on the x-axis, where we can test processes like convection and core overshooting. The convective core is shown in blue with an extension of the core by overshooting in the blue hatched region, and this is a small fraction of the pressure scale height where particles continue to move past the convective boundary, dredging more hydrogen into the core and prolonging the main sequence lifetime. In this case, a small amount of overshooting is implemented by a fraction of 0.1 on the right and 0.5 on the left. The key difference is the presence of these white semiconvective regions, which open up due to unstable convection and a positive chemical gradient. This is a slow diffusive process which acts as an inefficient convective layer and keeps the star hotter and bluer. If the core is too large, then the semiconvective regions don't have enough room to develop, so we must include a minimum amount of overshooting. And by probing the indirect effects of mass loss on the structure of massive stars, we find that the evolution towards red supergiants may be heavily affected by metallicity-dependent winds, providing insights for mass loss mechanisms. We now have a unified set of parameters which is able to reproduce the HT limit for all metallicities by implementing minimal overshooting to allow for semiconvective regions to form and highly efficient semiconvection to favour bluewards evolution above the HT limit. The standard Vink mass loss prescription indirectly dictates the change in blue or red evolution because of the remaining envelope mass. If we look at these structure diagrams for 60 solar mass models in the Milky Way, LMC and SMC, the amount of white semiconvective regions increases with decreasing metallicity due to metallicity-dependent winds, naturally providing a higher HT limit at higher metallicities because of the red supergiants, which can form at luminosities up to log of 5.8 in the Milky Way. So due to the limited number of observations with increasing mass, the upper luminosity limit of red supergiants may be challenging to resolve. And as a result, we also investigate the time spent during core helium burning as a blue supergiant or red supergiant, finding that the upper luminosity limit may not be a hard border, but rather an observational artifact as a result of short timescales. So to provide a theoretical HT limit, we've shown here the percentage time spent as a red supergiant during core helium burning for all masses and metallicities with our new unified set of input parameters. We can see a distinctive change in behaviour from the Milky Way to the LMC and SMC, and this switching represents the change in envelope mass determined by the extent of mass loss, allowing semiconvective mixing or not. In the Milky Way, our models show a theoretical HT limit at around 5.9, and in the LMC and SMC we find a theoretical HT limit at around 5.5 as is observed. So we found that while mass loss did play a key role, it was actually the indirect effect on the envelope structure which prohibited semiconvective regions, which would promote bluewards evolution above the red supergiant limit. And in this study it was important that we included low overshooting to allow for additional, or in this case semiconvective mixing to take place, while it could be the case that another type of mixing is taking place. In fact, Gautam, a PhD student within our group, is continuing to work on this with new observations suggesting a possibility of a metallicity independent HT limit. So look out for his talk at this meeting as well. So we find that the combined effects of low overshooting and efficient mixing in the envelope, that the standard metallicity dependent mass loss naturally reproduces the observed HT limit at each metallicity.